Okay, so this is the little introduction on statistical inference. And I'm actually going to go a little bit more into the material than the usual kind of business sections. I'm just going to go through some generalities of hypothesis testing, and then these will be expanded on the individual videos where we're going through for the different techniques. So this chapter is all about statistics, and statistics is basically we're making inference on a population using a sample. So that's all we're doing. And let's just I'll just go to my little example. I got this from kind of a marketing example. So imagine that I work for Walmart and I want to sample US Walmart shoppers or just US consumers, adult consumers in general, about whether they would actually be prepared to give up, they would be prepared to pay for plastic carrier bags, reusable bags for the sake of the environment. And we might want to do a test, of how much on average these consumers would be willing to pay. And obviously we can't kind of sample 100, 200 million consumers. So we might sample 1,000 consumers, and then we would like make inference on the overall mean based on our sample mean. So we're using our sample statistic, which is the mean in our sample. So it might be, for example, on average we'll pay 5.2 cents, and we're using it to make inference on the population value, is this more or less than 5 cents? So that's just kind of statistics in a nutshell here. And this little diagram is just, this is a little bit beyond what we're talking about, but the idea is we have a target population. We try and find some list that approximates that population, and then we create a sample from that population. Another great example, of course, is kind of in politics where we are sampling, we'll do a sample of maybe 1,000 people and say the last election, we're looking, what percentage of people are going to vote for Joe Biden and what percentage of people are going to vote for Donald Trump. And usually those percentages are given, for example, plus or minus, say, 2%. That's an example of a confidence interval. And we have our sample value, maybe 46%. And we're saying we think the population, based on the size of the sample and the variation, is maybe between 44 and 48%. Okay, so we'll just talk a little bit about this idea of hypothesis testing. And a hypothesis test, we have kind of two states of being. We have the null hypothesis, which really is we're trying to prove against. The null hypothesis is our state of being, and our alternative hypothesis is something that we try and prove. And we're trying to basically gather evidence to reject our null hypothesis in favor of our alternative hypothesis. So it's like we have two possible conclusions. We have enough evidence, so we reject the null hypothesis, or we don't have enough evidence and we fail to reject the null hypothesis. So let's just give a few simple non-numeric examples. I'll start with the book one, and then I'll kind of give one of my own. So we assume in the legal system that well, at least we hope we do, that everybody is innocent until proven guilty. And in the course of a trial, we gather evidence to try and prove that someone's, at least the prosecutor, to try and prove someone's guilty. If we have enough evidence, we reject the null hypothesis and find this person guilty. If we don't have enough evidence, we fail to reject and we can kind of consider the person to be innocent. So here's my little example. I thought since we had the Super Bowl a couple of weeks back. So every time somebody scores a touchdown, it's reviewed to see whether it's a touchdown. And basically, the video judges are trying to gather evidence that it's not a touchdown, i.e., we're looking if somebody's feet were out of bounds or they didn't catch the ball properly, or they maybe committed a foul by pushing someone. So here our null hypothesis is the touchdown stands, and we see if we gather enough evidence to say this is not a touchdown. If we have enough evidence, then we say it's not a touchdown, the touchdown is nullified. But if we don't have enough evidence, then we keep the touchdown. Okay, so this kind of introduces another concept, and this is the concept of the type 1 and the type 2 errors. So a type 1 error, which we use in statistics to actually determine the strength of our test, the type 1 error is our proportion. Given that the null hypothesis is true, it's our probability of rejecting the null hypothesis. So in this case, it's our chance of when we have a touchdown. Maybe it is actually a touchdown, but the type 1 error, which we call alpha, that's our chance of, rejecting the touchdown regardless. The judgments might be flawed. So imagine that the null hypothesis is true and it is a touchdown. Then if we fail to reject the null hypothesis, then we make a correct decision. So the touchdown stands and we've done everything correctly. If it is a touchdown, but we actually still reject the null hypothesis in favor of the alternative that's not a touchdown, then we've made a type 1 error in that we've rejected when we shouldn't have rejected. Now, the converse of that, the opposite, is if in fact it isn't a touchdown, but we don't reject, so it's not a touchdown, but we say, yeah, we're keeping the touchdown, then we've committed a type 2 error. Now, in terms of probability, we call the type 1 error alpha and the type 2 error beta. Now, the type 2 error is a little bit more complicated because depending on how strong our alternative hypothesis is, it could be in this example, maybe it's just a very minor problem. Like we have 1 foot slightly out of bounds. But we might also have something which is a very strong alternative hypothesis, i.e. we push a player illegally in the back while we're trying to catch the touchdown. So the type 2 error sometimes depends on how strong the alternative hypothesis is. But anyway, if the alternative hypothesis is true, but we fail to reject, then we commit the type 2 error. And again, if the alternative hypothesis is true and we reject, yes, we've done it correctly, i.e. the touchdown is rejected and it's not a touchdown, then again, we've made the correct decision. So I got this from a different textbook. Note this textbook uses slightly different terminology. I actually prefer fail to reject rather than accept. But the idea is these 2 corners are correct decisions and the other 2 corners are incorrect decisions, which are the type 1 error and the type 2 error. Okay, so what we're going to do in each of these tests, and in each of these tests we're going to do it in some detail, is we first determine the population parameter. So in this case, this could be the population mean. It could be the mean amount of people the mean amount that people will be willing to pay for reusable bags in Walmart. It could be the proportion of people who are going to vote for a certain politician, or the proportion of people who would vote to legalize marijuana. It could be, for example, the difference between 2 means. So it could be, imagine we have 2 groups of managers, and maybe one group of managers has very strong social networks online using LinkedIn, and one group of managers does not have that strong social network. We want to look at the difference in performance between the 2 groups of managers, and our population parameter we're interested in is the difference between the 2 means of performance. We select a level of significance. So this is the type 1 error. We're basically doing the strength of the test based on how much type 1 error we're willing to have. And we'll talk about this more technically in terms of alphas, when we do the actual tests. We determine an actual rule. So in our non-technical example, it's like, how much evidence do we need to reject the touchdown? In statistics, it's how much statistical evidence do I need to reject my null hypothesis? Once we have our rule, we collect our data, we calculate our test statistic, we compare it with the decision rule, and then we make a conclusion. And this is probably a little bit too philosophical for this course, but it's from the book, so I thought I'd keep it. And the idea is we're assuming the null hypothesis is true. We can't really prove that it is true. We're just trying to see if we can get enough evidence to reject it. And if we don't reject it, we just say we don't have enough evidence to reject the null hypothesis. So if our null hypothesis was the mean amount spent by the mean willingness to pay for reusable bags is 5 cents. If we're really close to 5 cents, maybe our average is 5.01 cents, then maybe we don't have enough evidence to disprove that it's 5 cents. But at the same time, we can't really say it's exactly 5 cents. So that's kind of don't worry too much about this. It's more of the philosophies of hypothesis testing. And in this class, we're just more worried about the practicalities and the practical results for hypothesis testing. Okay, so here's a little selection of what we're going to be covering in this chapter, and just some hypotheses to go with them. So a single test of mean, we're basically seeing if a mean is a certain point value. So here's my little business example. Retargeting consumers via banner ads has a return of investment of $10 for every dollar spent. That's the null hypothesis. Now, depending on the type of alternative hypothesis, whether it's, and we're going to talk about this in the individual videos, we could look in one direction, a one-tailed test. So we could see whether it's less than $10 or greater than $10, or whether we're looking in both directions, not equal to $10. So there's kind of 3 different alternative hypotheses, but they're all just testing, trying to prove that the return on investment is not equal to $10. So we can also test that. I gave that example of the managers having different kind of success metrics, but here's one on the same kind of domain as the previous example. So Facebook advertising has the same ROI as keyword advertising. So maybe we give like multiple advertising campaigns. We have some via Facebook, some via keyword, and we measure the ROI. Then we will compare the mean values for each. So Facebook advertising is the same ROI as keyword advertising. And again, we can have these 3 different alternative hypotheses. We can check in one direction less or more, less or greater, or we could check in both directions and say the advertising is different. Facebook advertising is different from keyword advertising. So here's another few. We could test a correlation, which we're not doing in this chapter, but we'll probably do in regression. So we want to say we're testing if movie revenue is related to pre-release social media buzz. And I've got a data set. I'll kind of maybe do that in the regression chapter, which has pre-release social media buzz in terms of tweet rates per hour and opening weekend movie revenue. And the null hypothesis is these things are just not related at all. So the movie revenue is not linearly related to social media buzz. And the alternative hypothesis is the revenue is positively, negatively, or just when I say linear related means either positive or negatively related to pre-release social media buzz. So here the null hypothesis is we're not related. There's no type of linear relationship. And the alternative hypothesis is there is some relationship, whether it's positive, negative, or in either direction. And lastly, we're going to look at a test of association of qualitative variables. And we're going to see And my little example is, imagine that we have some sort of maybe cell phone gaming app, and we're worried that we have very low awareness among female consumers. So we want to see if gender is independent, i.e., not associated with brand awareness, or whether gender, the alternative hypothesis we're trying to prove, is gender is dependent. There is some relationship between gender and brand awareness. Maybe that males are, 70% of males are aware, and only 30% of females are aware of my particular brand of cell phone gaming. So these are just some kind of little examples I put together of different kind of types of hypothesis tests that you're going to come across in this chapter and further on. Okay, so now let's move on to this little business section of the talk. Statistical testing, when it comes to business, this often comes under the boundary of what we call A/B testing. And this has become something of a buzzword. And it really was developed on this idea of comparing, from Google, comparing different kind of web pages, but this term has now become more widespread in industry. So here I'm going to take it straight from the horse's mouth or from Google. I've got a link here if you want to click on it. An A/B test is a randomized experiment using two or more variants of the same web page. For example, we want to test whether we want to change the color of one of our buttons will increase our revenue. So here's a little example, and here we're testing, we have two variations of our website, and we have the first one here and the second one here, and we want to see if the conversion rate is higher on the first or higher on the second. And we can do a simple two-sample statistical test to prove whether it is or is not. So you imagine we could do all sorts of things. We could maybe look at average revenue. We could look at like bounce rate, how many people jump off the website. But the idea is that Google is actually doing this test for you. It's sending, 1,000 customers to website 1 and 1,000 customers to website 2. And then you can record the results and you can do your statistical test, i.e. A/B testing. Now, here's a nice little article. I found this on, Harvard Business Review from a recent blog post, so definitely check that out. And it's saying, this sort of statistical experimentation, is it really useful in business? And it's saying that, well, yes, it can be useful, i.e. the previous examples. And quite often building this culture where if you're developing a new product or a new website, you do some sort of rigorous testing that builds this culture of experimentation, and it can help you kind of optimize your processes and your products. And the idea is, even if we don't actually prove a scientific hypothesis, just by doing some descriptive analysis, for example, the previous example, we could maybe do a bar graph, some charts of conversion rates. Just by thinking about a scientific process, even without statistics, then we can gain some sort of insight into our data. Another thing to note is that if we have small boosts in our kind of optimizing things like conversion rate, or if we can kind of do a pricing experiment and we can optimize our prices by 1%, quite often small boosts in these variables can lead to much bigger increases in profits, due to kind of multiplication of kind of marginal rates. You just have a little bit extra retention. This can really kind of increase your profits by quite a large amount. We need to think of certain things. We need to think about, what sort of metrics we need to use in our experiment. For example, if we're trying to optimize revenue, do we actually use sales? Or maybe do we use something like long-term customer lifetime value? What exactly are we trying to optimize? Another thing we need to think about is that often corporate data have very bad data quality. So if we're doing these experiments on our corporate database, i.e., for example, CRM systems, and I remember working with CRM systems, and I don't want to disrespect salespeople, but quite often salespeople just a load of junk, the same contact in multiple times in the database, and we end up with a mess of a database. So if you have bad data quality, it can lead to faulty results and conclusions. So here's my second business example. And something very relevant at the moment is clinical trials and clinical testing. Here, the degree of rigor, because we have regulatory standards, is probably a little bit higher than website A/B testing. But it's a huge, huge market. The market for global market for clinical trials was worth over 40 billion as of last year. And I can imagine with COVID, this might actually have increased. I saw something by 2025, it's estimated to be about 60 billion. And I found a nice little article, and I'll read this out. It just points out that the need for rigor, it's not just about doing, does this drug perform better than a placebo drug? We need to use rigorous methods. We need to define a research question. We need an experimental design, a well thought out experimental design. We need to plan our experiments before we implement them. So we have to have rigor at all kind of stages of the clinical trials. And just for kind of interest here, I found from a UK site, if I use somebody else's graphics, I always like to cite them to claim fair use. And it talks a little bit about the process of clinical trials, how we go through phase 1, i.e. says young, healthy people, probably poor students who need the money and would actually, be kind of would be more happier to risk the side effects, kind of young and stupid, I guess. Then we have more people affected by the specific disease. Then we finally have a very large phase 3 trial, large numbers of people over long periods of time, multiple geographical areas, hopefully a little bit safer because we've probably ironed out severe side effects in phase 1 and phase 2. And eventually we go to licensing. And then once the drug is released, for example, the COVID vaccines, we want to be testing for things like adverse reactions, how effective things are, whether effectiveness changes over time, i.e. COVID vaccines have got less effective with the new variants. So there's still a lot of scope for statistics here. Okay, so my final little example, we're going to talk a little bit about experimental design. And we don't really go into too much detail here. We're going to be looking at ANOVAs in this chapter, where we're looking at very basic experimental designs. But where we have multiple factors we're testing, we have a dependent variable, and we want to kind of improve maybe our product or improve our process using this process of experimental design. So my little example here is we want to maximize the taste of beer, and we vary the amount of grain, hops, yeast, water, and the fermentation time. And maybe we have high and low values of each attribute, which would give us 32 different possible beers. We test those beers, or maybe, if we have lots of attributes and we have hundreds of beers, we will test a certain subset of those beers. And the subset we choose, that's the type of design we use. That's kind of some of the technicalities of experimental design, which in reality, you probably need an entire class on experimental design. We're just kind of cover the basics in this class. But the idea is we have these independent variables we're trying to test. We've got a dependent variable, i.e. how good the beer tastes. We want to kind of optimize the taste by varying these different parameters. Here's another example on the same kind of idea, and this is kind of conjoint. This is from marketing. This is conjoint analysis or trade-off analysis. And this is kind of something from my kind of little area of quantitative marketing. And the idea when we're designing a new product, we would all love this incredibly powerful smartphone or computer at a very cheap price. But in reality, things don't work like that. There's usually a trade-off. We can have something more powerful for a cheaper price. Or maybe if I don't care about computer graphics, but I do a lot of math work, I could have a very strong processor, but maybe not as nice a monitor. But if I like computer gaming or I work in graphics, maybe I don't care about the processor as much, but I want a really nice monitor. So there's going to be a certain trade-off here. And what we would do is we would show consumers lots of kind of choices, trade-off choices. So here this consumer's got a choice of 3 PCs, and they choose which one would they prefer. And then we would use ANOVA, a similar technique, to kind of relate these different attribute values to consumer utility. So we could maybe say, for example, what's the utility gain over 2 GB of RAM, over 1 GB of RAM? And then we could actually relate this to prices. How much would consumers pay for an extra gigabyte of RAM? And here's a little example of conjoint analysis. This was this is going back a long time ago, but this was one of the first commercial uses of conjoint analysis. And this was Courtyard by Marriott. And conjoint analysis was used to help design the concept for the hotel chain, in that there were lots of those big consumer surveys, and they could survey consumers on things like bed hardness, TV, gym, room service, laundry, layout of the hotel rooms. And they used this conjoint analysis of trade-offs in consumer preferences to be able to design the perfect hotel chain for their target market of maybe your average business traveler. So that was kind of my last little example. And then the individual videos, each video will kind of go through one of the different techniques. Okay.